Everyone, this is a video demo and a tutorial in the same time, and the idea of this video is to help those who wish to replicate the circuit and observe the effect. And people are having a difficulty understanding what's happening and why it's important to have certain resistor values and capacitance values, and this demo here will guide you, hopefully, to better understand how this circuit is functioning. Now, for this tutorial and demo, I'm going to use 120 volt grid voltage here, and just for simplicity, and we'll look at what is happening in the circuit. And I still have my generator here ready and cushioned. And once we see what happens here in the circuit with the oscilloscope, we will put it on the generator and see what the effect is there. So right now I have, like I say, 120 volts coming in here. Everything's pretty well isolated. I won't get a shock or something unless I touch across the resistor there. So on the grid we have a hot side, which is this black wire, and the neutral side, which is the white wire, and that's the traditional way it is here in Canada and most likely the United States as well. So our hot side is coming into the circuit here, and we have our voltage probe there measuring our voltage coming in, and that's just so that you don't see all the wires all over the place, just to keep it neat. So basically straight directly to our resistor here, and that resistor is a 1.5K, so 1500 ohm, 5% accuracy, and that's a 25 watt resistor. And then again, now we have our next wire just going across here to what is our current sensing resistor, also known as a shunt, and that's a 10 watt 0.1 ohm resistor, 5%. And we have our scope probe across that resistor there as well. So this is just a completion here now to the neutral. So hot, just basically across, returning to the neutral. And we'll always be keeping this same configuration of circuit. All we'll be doing though is adding some capacitors on this side, and that's all that will change. Now if we look at our oscilloscope here, which is what is very important, here in the yellow we have our voltage, and our voltage is at 122 volts at this time. That's coming in from the grid. So, and then here in the blue we have our current, basically, which is the voltage across that 0.1 ohm resistor. Now this is a resistive circuit, and in a resistive circuit you're just going to consume power, because basically it's a short circuit across a resistor. And this scope has a math function that can calculate the power. So as you see here, our voltage and current are together, so they're in phase, and that's what happens with a resistive load, and therefore the power is just basically consumed. And this is reflected by the calculation of power here being on top of the scope 0 line here. That's why this goes up on top here. So if we look, we have 122 volts coming in, and that's our voltage across our little current sensing resistor of 0.1 ohms. And this is the mathematical calculation in watts, basically. That is equivalent to watts. And that is 9.88 watts, okay, going across our 1,000, oops, it's a little hot, 1,500 ohm resistor there. And if you do the math, you will calculate 122 volts will come up to exactly that 9.88 watts. And I have here my laptop, and this is a very handy program. It's called Electronics Assistant, and in there you have a power calculator, And here I put 122 volts. I select resistor, and 122 volts on a 1500 ohm resistor. That gives us 9.9 watts. And that is exactly what our scope is calculating there. 9.87, that's basically 9.9 watts. And I've displayed this here as our maximum, and our minimum. The minimum is nothing, it's in the millivolts. Basically that would be displaying whatever is being returned. And this here is basically, it's just consuming power. So that's all the top section there. That will be for later, so that we can look at that once we add a capacitor. So now what I'll do is I'll just pause the camera, and I'm going to add a capacitor before this. Oh yeah, before we do that, there is a user called .99, or a researcher that's called .99. He has been quite adamant about inverting the channel 2, which is our current sensing resistor. So right now I'll do that for you. I'll go to channel 2, and we will select invert. It's off now, and we'll select invert. And now we will go back to our measurements. Now if we invert our channel 2, basically now we have a reversal of everything, and that math now is saying we are returning 10 watts, and our maximum is basically 0, and our minimum is the opposite. So basically by inverting that probe, we are reversing everything, and as far as I'm concerned, that is not the way to calculate that. So this video is also helpful to conclude that that is not the correct direction, and that would not help the circuit. And we are not changing the circuit in any way. We're just going to be adding a capacitor between this on the hot side here, between the resistor. Everything else will stay the same. So obviously using invert is not the correct approach for calculating the true power in this circuit. So now we will go back here and adjust that so we have that off. And now we are seeing go back to our measures. Now we're seeing it the correct way, and we're displaying the correct amount of power being dissipated on that resistor there. So I'll just pause the camera now, and we will add a capacitor right there. Actually, before I do that, I forgot. We know that now we are consuming 10 watts here in this circuit, and we can now detach this from the grid. You see we got 0 volts there, and what we'll do is we'll connect this to the generator there, and I'll start up the generator. There's our watts that the motor is going to be consuming. We're at 0 watts, and now I'm starting the motor here. I've got to give it a spin sometimes to get it going. So if we look now, we're using about 158 watts in average, and the circuit is off, and I will turn on the circuit now. So now it is on, and if you look, we're now using about 167. So basically we've now added our prime mover for this generator is now actually needing another 10 watts to power this load here. Now it only outputs about 112 volts. It's not capable of outputting as much as the grid. So if you do the math at 112 volts across that resistor, the scope is kind of viewing it here. We now have about 8.65 watts there. And if we go back here, we're at 164, and I'll turn off the circuit there. And there you go. So now it's hovering around 156 watts, and that is the difference. So obviously you see this circuit is just using power when you turn it on, and it's using pretty well exactly the same amount of power it's dissipating against that resistor. Alright, so I wanted to show that before we go and add the capacitor there, and let's do that now. Okay, so now I've just broke my connection here directly to the resistor, and now I have a capacitor added in series to the resistor, and there's the other side of the resistor. That's my connection here to my voltmeter here, those two across. So the circuit has not changed, okay, except adding a capacitor in series pre the resistor here, which is the load. Now, if we look at the scope shot, we will not see anything fantastic. There is no amazing result by just doing that. Okay? So if we look, we have a little bit of a phase shift now between our voltage and current. Okay? And we can see our math is just starting to dip down a little bit there. But this is nothing exciting. And we have basically 122 volts still running through there. Our current is, there it is, across the current sensing resistor, and the math is saying we are now having about 8.3 watts being used on this circuit. And if we look at our voltage now across our 1500 ohm resistor, we're at 113 volts. So if we go to our math here and we now re-enter 113 volts and we look at the results, we have 8.5 watts across. That's what it comes to. 113 volts is 8.5 watts, and what our math here is telling us is it's calculating 8.3 watts. So we're all still in the same ballpark, and that's what's happening there. And I don't have to test it, putting it on the generator as well. I know this circuit, the way it is, will consume power from the generator, at least that amount of power, which is 8.3 watts there, which is this figure here. So the means is the true amount of power that is being used, and that's what this scope can calculate. Now, the next thing I'm going to do is I'm going to change this resistor. So just the resistor value. The capacitor will stay the same, and I will be adding a 10 ohm resistor, and this resistor here, you've probably seen it in other videos. I had to take the autofocus off of the camera anyways, because it would just cause problems. So you have to trust me, this is a 10 ohm resistor, 1%, and it's rated up to 50 watts. So we're going to be changing that there. That's the only change now. Okay, so now things are identical. The only change is we've now changed this resistor to a lower value. Alright, and basically now we have 2.25 volts across that resistor, and this is the change now. So that makes a drastic change in the circuit. And now if you look, we still have that 122 volts going in. We have a lot more current going across our current sensing resistor, but the big difference is now we have a very large phase shift between the voltage and the current. And that phase shift to me looks to be 90 degrees out of phase. And if we look now, our math is going to calculate the true power, because based on the phase shift that has happened. And it is now saying that it is actually in the minus, okay, minus 3.15 watts, meaning that it's actually returning 3.15 watts to the grid, and there is its maximum calculated on the upper portion here of the zero line, and there is its calculation here on the bottom of the zero line. So you can see that that's reflected there as well. We now have a minus 45 compared to a minus 24 here. But what is important is the math calculations here on the means, and that's truly the power that is happening here. So this circuit is actually sending more power back to the grid based on this phase shift that the capacitor there is causing. Now what we can do is, well, we only have 2.25 volts there, and if we now go and add that 2.25 volts and we change our resistor, we now have a 10 ohm resistor. We're not getting an amazing result. We're basically getting 500 milliwatts there. It's nothing, okay? But we've just added a 5 microfarad capacitor, basically. So now what we can do is we'll disconnect our capacitor. I'm being very careful here. This is live, and we're going to just basically first just jump to double the capacitance. So these two are connected in parallel, and but though my circuit then is connected in series across that capacitor. So we are now connected, okay, and the only thing is that now instead of being 5 microfarad, we now have 10 microfarad of capacitance, and now our resistor has basically doubled. So we now have 4.48 volts across that resistor, and if we look here at the math, I'll have to make some adjustments here so that we can display everything correctly, because it does change. So still our voltage there of 122 volts, and then our current sensing resistor is sensing more current going through the circuit, but it doesn't really matter, because still we have a huge phase shift between the current and voltage, and that's what's important. And when you have that phase shift, you're not using any real power. You're just circulating power through a circuit, okay? And if we look here, our upper portion of power being used is small compared to the lower portion of the power being returned. And if we look at our math, it's now saying we are actually returning 5.4 watts back to the grid, and here we are, there is our data here, so we have basically, you know, around 50 on this side, and we've got about 80 on that side here on the bottom side. And that is the interesting part. So as you keep increasing the capacitance value here, you're going to get more and more power across your load resistor here. And now what I'll do is I'll tune it so that we can actually have basically 0 watts here, or close to nothing as far as watts is concerned, to see how much power we can actually get out of that 10 ohm resistor. So now I'm going to just jump and go to a huge or much larger capacitance value to maximize the power we're going to dissipate across that resistor. Now before we do that, we'll just go here again to our program, and now I'll enter our new data, which is about 4.5 volts, so 4.5 volts across our 10 ohm resistor. So now we are dissipating 2 watts, and we're not using any real power from the source. And what I can do is I can connect it to the generator, but actually I'll wait till I have it outputting more power, and we'll just test it on the generator to see if it causes a load to the prime mover. As it is now, it's only 2 watts we're getting there basically, and I know it won't affect the prime mover here, and we can add more capacitance and get more power across our resistor there. So that's what I'll do right now. And okay, so now we're back and I have a total of 35 microfarads now added to that side, and now there's a shift in balance, and now we are actually taking a little bit from the grid, and what we are dissipating across our 10 ohm resistor is 15 and over 15 volts, and now we're starting to actually get into some real good amount of power. So if we look at our scope shot, there is again all the data. So obviously we're getting into more current circulating through the circuit, and that's fine as long as we don't really need to pay for it. So the math, because it's again 90 degrees out of phase or a little less than that, the math now is starting to calculate the differences between what is taken and what is returned, and now you can see that the math is saying that we're taking actually half of a watt, so 500 milliwatts is what is being used, and there is the upper portion and there is the lower portion, and so that is kind of interesting to see it all in this way here that I'm showing you the effects. So basically the capacitance value and the resistor value have a huge amount of differences and effects to bringing the circuit into a positive direction versus a negative direction. So as you saw with our high resistance, we don't get any positive effect, but when we drop our resistance and we add our capacitance, we can get this into getting a good amount of power out. Now the other thing you could do here, and you should be able to quite put that together, is if I want to get more power out, I would again have to drop the value of this resistor and then continue adding capacitance, and then I could actually boost it up. So what we'll do now is look at the amount of power we are dissipating in that resistor, and I entered that. We have 15 and a quarter volts across our 10 ohm resistor. That means we are dissipating pretty over 23 watts there. And now what we'll do is we will connect the circuit to the generator, and to see if that 23 watts will affect the generator. Start the generator there and connect the circuit in, and we will look at our wattage. And now we'll turn on the circuit, and as you see, the power is going down when the circuit is operating, because we actually have less voltage coming out of this generator. So we now only have 12 volts across our load, and this is what the scope data is showing. And the reason why this is going down is because the circuit is tuned to be off the 122 volts from the grid, and we're only outputting around, it says 97 volts the way it is right now. So what we'd have to do is add more capacitance here, and we can bring that resistor well over 15 volts. And I've done that before, and the ideal tuning point of this generator here, the way it is I can get 30 watts out of it without affecting the prime mover, meaning there's no need for extra current or watts to go into the system for the amount of watts you take out. So there you go, you have a proof. And then like what happens is when the circuit is tuned the other way around, it actually relieves the prime mover. So as you see now, it's taking only 137 watts, and I'll turn the circuit off. And now you see it's loading the generator, so 154, 155. So it's actually returning power back to the generator, which is helping the alternator actually move. So that recirculating energy is now actually hitting back in the alternator there and pushing it in a favorable way. So it's your choice. You can either do that, or which is regenerative acceleration, and then or you could just maximize the amount of power on your load by maximizing the amount of capacitance that you add here. And I'm not going to bother doing that because you should understand the results by adding more capacitance there. This will come to a point where it'll be basically zero difference, and we'll have more power on our load. So that is this part of this video, and I think that'll be long enough. And the next part, I will show you the results of doubling the input voltage, and that is also a benefit. So before we okay, now we're back, and we have the neutral removed here. So we're just using the hot on this side here, and the circuit is identical, the same 35 microfarad of capacitance, the same resistor, and our same shunt. The only difference is I've come on this side here, taken the other side of the panel, and combined it there. And our resistor is getting very hot. I have to now moisten it with this white Kleenex that has water on it to keep it cold, and you can hear it fizzing away there, or to cool it down. We are now dissipating 30 volts across that 10 ohm resistor, and I'm going to try to save that resistor. I don't want to destroy that. And right now there's steam coming out of there. You can see that steaming up the lens. And if we, sorry, steamed the lens too much there. If we look at our maths, we have 245 volts now going across the circuit, through the circuit, and a huge amount of current as well. But that's not really important. Still, we have maintained our 90 degrees phase shift. And if you look at what's really important here, is here we have milliwatts that we're using, okay, like under half a watt, so basically 300, 400 milliwatts. And there is our max, and there is our minimum. And this is real. You can see that we are dissipating a real amount of power there. And if we do our math, 30 volts on that 10 ohm resistor, you will see that we are now dissipating 90 watts. So there is the huge benefit by inputting higher voltage, and we are still maintaining our phase difference. And that is the secret. And I'm going to unplug this because things are getting a little out of hand. I don't want to lose that precision 1% resistor there. I'll flip this around because it's got no water probably left on it. It's a little too hot. Actually, this whole thing is dried up now. Anyways, so you see there, obviously we definitely have our true 90 watts. Don't be fooled by naysayers that this is not real. We are not really dissipating any real power across that resistor. You just saw it. It just boiled away. That Kleenex is close to being dry right now, and it was like totally saturated. And it's, you know, it's this thick of Kleenex material. So Unfortunately, I can't hook it up to the generator because this generator is only 100, barely 100, over 100 volts. If I had one that has 220 volts output, we should be able to get the same kind of performance. So the next video, which will be also a tutorial, will be showing you how to do this same thing except using an induction motor. So there's huge benefits with using higher voltages, and it doesn't use any more power to do that. So what's really important is to have low resistance and high voltage, and that's where you start getting these really interesting benefits. As you saw, things got pretty hot here, and it takes no time for this change to occur, basically just by doubling our input voltage, and we more than double our output. So that concludes this video tutorial and demo, and hopefully this has enlightened you and given you the correct direction to take, and that's why I am doing this. And I hope you appreciate me sharing this and giving this away. So thanks for watching, and look for the next tutorial that is going to show you how to use this effect and turn it into mechanical work to your advantage. Bye now.